look at this.
Or whatever, change that line. So we can turn all of these knobs in our model until we get the best possible fit. When we do that, about 85% of all matter universe is atoms. It's this other stuff. All right, going back to the theme of questions. I hope I've convinced you that you shouldn't really convince dark matter exists, but you take my word at it, the cosmology is perfect. If anyone can convince you of something that complicated in 5 minutes, here. But we're convinced. And you should take our word. So the thing we'd really like to know, and the thing that I would really like to know and have spent the last 15 years or so thinking about, is what is this stuff that we call dark matter? A kind of a companion question is this dark matter's out there and we can't see it. Why can't we see it? Why is it so dark? Or if you turn the question on its head, why is ordinary matter so bright? Or why can we perceive ordinary matter? When I look at that podium, why is it giving off light that my eyes can detect? And for that matter, when I put my hand into this wall, stop. Why do I feel this? Why doesn't my hand just go straight through that wall? After all, my hand is basically empty space. The fraction of the volume of my hand that atoms are actively occupying is minuscule. And that same thing is true about the wall. So when I put my hand into the wall, you might have expected that my hand should have passed straight through it. But it doesn't. Does anyone know why? Unless you're in the first 10 rows, I can't see your hand. So, here. What's that? Electromagnetism. So it turns out that there's a lot of stuff with electric charge in my hand, the protons and electrons, and in that wall. And when I push my hand towards that wall, those electrically charged particles push against each other. And that prevents my hand from going through the wall. So it turns out that the reason light is emitted, reflected, or absorbed by stuff is because stuff in it has electric charge. Something without electric charge will be dark. And ordinary matter is bright because it has electric charge. Kind of generalize this argument, think about the 4 forces that physicists have identified in nature. By far the weakest of these forces is gravity. It's basically not measurable in the laboratory. You can barely tell there's gravity between atoms. Like, it's extremely feeble. And then there's the electromagnetic force that we were talking about. There's also the strong force and weak force. These you only notice in subatomic physics, for the most part. The strong force, though, as its name implies, is very strong. If dark matter interacted through the strong force with atoms, we would have detected it a long time ago. So what we learned from this is whatever dark matter is made of, whatever kind of substance it is, it better not feel either of these 2 forces. It can't have electric charge, and it can't have the stuff we call color. It's not the kind of color that you know about, but it's the same word as it's the thing that makes you feel the strong force. Whatever the dark matter is made of, it can't feel these 2 forces. This chart shows every kind of matter we understand in the universe. Okay, so all the stuff on the periodic table is made up of these guys, basically, along with the electrons. These 6 quarks are all the things that are strongly interacting in nature. These 6 leptons include the well-known electron, the neutrinos that you've probably heard of, and a couple of other particles. And then these are the particles that carry forces. The photon is why there's electromagnetism. The gluon is why there's a strong force. The W and Z is why there's a weak force. And then there's the Higgs boson that's been all over the news and was discovered a couple years ago at the Large Hadron Collider. Let's contemplate for a second whether any of these known types of matter or energy might make up the dark matter. Well, the first thing we can do is rule out anything that feels the electromagnetic field. So I've crossed out everything in the chart that has electric charge. That's a lot of it right off the bat. That simplifies the problem. Now let's carry it 1 step further and rule out everything that feels the strong force. And again, the quarks get doubly ruled out. The gluon's gone now. And we're left with a few options, the Z, the Higgs, and the neutrinos. But now we also have to require that the dark matter is stable. And that rules out these guys, the Z and the Higgs. What I mean by that is if all the dark matter were made up of Higgs bosons today, tomorrow there wouldn't be any dark matter. The stuff decays in a fraction of a second. It doesn't play the kind of role we're hoping to play. And we're left with only the three particles that are called neutrinos. And they look like the kind of thing you'd want to make up the dark matter, except it turns out that they're really fast moving, or we like to call it hot. And that just doesn't look like the stuff we call dark matter out in the. So none of this stuff seems to do a good job of explaining the phenomena that we observe in dark matter. This might sound like a catastrophe, but where some people might have seen a catastrophe, particle theorists see a playground. I spend like several hours a day just brainstorming new crazy ideas of what dark matter might be. It's great. All right. This is a book that a friend of mine, Tim Tate at UC Irvine, made. It's his artistic impression of some of our ideas about what dark matter might be made up of. Some of these ideas are really well-motivated, elegant particle physics frameworks, like supersymmetry you might have heard of. Some of them involve extra dimensions of space. Some of them involve neutrino-like particles with even weaker than weak interactions, and many, many other things. The point is we have all sorts of ideas for what the dark matter might be. There's even a good chance that whatever it really is isn't on this chart or anyone's mind. We just don't know what it is, but we have lots of ideas. And what we really want to do is to find a way to test different ideas and eventually figure out what the characteristics of dark matter are and maybe where in this or whatever plot it might fall. We have three different classes of ways that we do experiments trying to test these different
こういう時に事故が起こる
kind of
ですよ。油断していると。丁寧に、丁寧に。安全に安全に。安全に安倍装備。安全に安倍装備。はぁ。なんかかっこいいね。
It's currently shut down, but it had been running for the last few years. It'll be running again at a higher energy later this year. It's a 17-mile underground tunnel. Around that tunnel, particle beams are accelerated by powerful magnets to, I think it's 99.9999997% of the speed of light. So virtually the speed of light. And then those beams are collided head-on inside of these giant machines. We call them particle detectors. Hundreds of millions of times a second. When you collide these protons together at such high speed,
靴の裏を研究するのもいいですね。
at one time, you can manufacture entirely new kinds of matter. So this all just comes down to the simple formula E equals mc squared. E for energy, M for mass. If you want to create something with a lot of mass, you put a lot of energy in one place at one time. You can create new things with mass. So this is how we discovered the Higgs boson a couple of years ago. This is how we discovered the top quark back at Fermilab back in the 90s, and all of those other particles we see in these charts. It's possible in the next run or other future experiments at the Large Hadron Collider that we could be manufacturing dark matter in a way that we could detect. The second class of experiments are what we call direct detection. And it takes advantage of a pretty simple observation. So do an experiment. We'll say, hold up your hand, put it down. If our leading particle physics theories are right about how heavy dark matter particles are, in that second, your hand was in the air about 10 million dark matter particles now. Okay? So if you could build a machine that can tell when a dark matter particle hits it, you could maybe see these particles simply by just waiting longer, being sensitive. So here's an example of such an experiment. We call it LZ, or Lux Zeppelin is what it stands for. It's in an underground former gold mine in Homestake, looking for the kinds of energy or radiation that are produced when they interact with each other. So this is a sort of depiction. So we have two particles coming in. They interact with each other, become destroyed or annihilate one another. And part of that reaction, they give off other sorts of particles or energy, and perhaps kinds that we can see, ordinary kinds. And you can try to detect this stuff with any variety of telescopes. Conceptually, it's very similar to a process you may have heard about before. If you take an electron and hold it in isolation, it's stable. Electrons will sit around forever. But if you take an electron and something we call a positron, the antimatter counterpart of an electron, and put them together, they'll annihilate very quickly. And when they do, they produce two photons with a distinctive energy, an energy of 511 kiloelectron volts. Okay? So every time you put an electron and an anti-electron together, they make this distinctive kind of gamma ray. This is what's behind, for example, the technology we call positron emission tomography, or a PET scan. The idea is you take something like a radioactive nucleus, like fluorine, put it into your body, let it produce occasional positrons. Those positrons annihilate with nearby electrons and give off this distinctive gamma ray radiation. And you detect those gamma rays and make them zap your brain. So we're essentially going to try to do the same thing with dark matter. So instead of looking for 511 keV gamma rays, we're going to look for a different kind of gamma ray that comes from the annihilation of dark matter particles. And this is the tool, this is the PET scan for dark matter. Okay. It's called the Fermi Gamma Ray Space Telescope. It's a satellite in orbit presently. It's been in orbit now for 6 years or so. It is, in my view, the greatest gamma ray telescope ever constructed by you. It's an amazing instrument. Here's its view of the sky. So this is the plane of the Milky Way. So that's where the middle of our galaxy is. This is straight north and straight south of that center. And you can see the whole plane of the Milky Way is kind of lit up in gamma rays. Here we go. Kind of lit up in gamma rays. If you could turn it 90 degrees, you would see the spiral arms and everything. But since we're looking straight into it, you can't tell. You see a number of features here, like this guy. This is a big bright pulsar that happens to be nearby. This thing is something called a blazar, which is a supermassive black hole, a very, very long way away from our galaxy that happens to be shooting particles in our direction. And you can see any number of point sources and other astrophysical objects in the map. If many of our particle physics theories are right, not all of them, if a large fraction of them are, you should expect under this map, if you could really dig deeply into it, a pattern that looks a lot like this. This is the one in the lower right. This is what dark matter annihilation should be. It's bright in the galactic center because that's where the most dark matter is. And it should produce a roughly round symmetric pattern of gamma rays that gets much brighter as you move in towards the center. This is the signal that we're going to be looking for in this data set. All right, so let me give you a timeline of how this story has played out so far. Now, I'm not going to give you the impression that this story has resolved. It is a long way from resolved. It is still very much up in the air, but it's developed a long way since the story started back in 2008. 2008 is when the telescope was first put into orbit. This is it's the vehicle that brought it into orbit. It's called the Delta rocket. This is one of NASA's main large payloads. And over a year later, the data that had been collecting to that point became publicly available. So let me explain what that means. That means that if any one of you had the wherewithal and ambition to study this gamma ray data, you can go to the Fermi website and download it and start working with it yourself. Probably going to take a while to figure out. It took me a long time to figure out how to do this. But it's there, and it's part of the public domain. Sometimes I'm going to be talking about the Fermi collaboration, and by that I mean the people who run the experiment, who built it, and who are kind of the caretaker of the data. But
ちだな、ここ。
So the data became public in August 2009, and then a couple of months later, just in August of the same month, Lisa Goodenough, who was a grad student at the time, and I wrote our first paper on this research. So
鎖
Lisa
場
was
を
really important
通
in
過
this
したんで
analysis because,
満足ですよ、今日は。
I'm not good at computing.
ねえ、
I
や
write
っぱなかったな、
code
今
in
ま
language
で。
that was written in
はしごはあ
1970s.
ったけど。
I plot in this
はあ、
antiquated thing called PopDrawer.
この程度でございます。
Yeah, I'm very, very old school in my computing, and Lisa helped bridge
なん
that
か乃木
gap.
坂の
Work together
生
very
駒さん
well.
とか、
She was a student at New York
鎖場やっ
University
て
at
ま
the
したよ。
time, but was spending a lot of time in
乃
the
木
lab
坂
and
とかさ
getting a number of good collaborations around that.
すごい。
Here's the paper that was out that October. Possible evidence for dark matter annihilation in the inner Milky Way from the Fermi Gamma Ray Space Telescope. We saw that just to kind of reiterate, we studied these gamma rays, and we found that the distribution on the sky and the energy spectrum were both well described by a dark matter annihilator. Okay, so it looks kind of like the thing we were looking for, and we thought that was pretty cool. Here's an example of one of the plots that appeared in that paper. These are all the gamma rays from the inner 3 degrees around the galactic center.